Okay, so let's start this morning's session. We have 3 speakers. Each one has 25 minutes, and I'll try to mark 5 minutes ahead of that. The first speaker is Àngels Ramos from Barcelona, and she will talk about K-bar-N chiral interaction beyond S-wave. Please go ahead, Àngels.
Okay, thank you, Abraham, for the introduction. Today we'll report on some work that has been done in collaboration with Albert Feijó, mostly by Albert Feijó, with the help of Daniel Gadda and Volodymyr Magas. Okay, I'm just merely the reporter. So let me start. Okay, let me see. Okay. Giving the outline of my talk, I will start first giving you a brief presentation of the K-bar interaction and how it is related with the S-wave lambda 1405 resonance, a brief history and some breakthroughs that have been done along the years. Next, I will move to present our chiral model, also how this model has been evolved over the years very briefly. And then I will jump into showing the new step forward that we have developed, which is including the terms that go beyond S-wave. I will show you the formalism, and I will present you the results in the K-bar-N sector. And finally, I will end with some conclusions. Okay, as you all know, the lambda 1405 dominates the behavior of the K-bar interaction in the isospin I0 channel. And actually, this interaction is able to develop a quasi-bound state, which is the lambda 1405, located only 27 MeV below the K-bar N threshold. Actually, this lambda 1405 may be considered the first pentaquark ever observed. Maybe the LSCB people would not agree with that, but the lambda 1405 is certainly a baryon that can be considered to be of the exotic type. Actually, in conventional quark models, baryons are thought as being 3-quark or QQQ states, but exotic baryons are pentaquarks. For instance, a type of exotic baryon is the pentaquark. It is composed by 5 quarks, and these 5 quarks can be in a compact configuration, or these 5 quarks can be more interpreted as being a meson baryon bound state or molecule. This is the image of the lambda 1405 that has been really is the nature of the lambda 1405 that has been achieved over the years. And let me remind you that in the late 50s and 60s, all this story began. This is the first stellar period of the lambda 1405. In that period, there was an intense activity in bubble chamber experiments at Brookhaven, CERN, and Rutherford Labs. And this experimental activity established the presence of a resonance with strangeness -1 around 1405 MeV. And since 1963, the lambda 1405 has become a particle in the PDG. But the idea that this lambda 1405 was a meson baryon molecule was originally proposed by Dalitz and Tuan in the late 50s. And they found they found actually a quasi-bound state from solving a couple channel Schrodinger equation that involved the K-bar-N and the pi sigma channels. Okay, what happened later in the 70s and in the 80s, there was a continuous experimental activity, again in bubble chambers and also in emulsions. There were cross-section, I have to go back, yeah. They were cross-section measurements, threshold branching ratios, etc. And in the theory side, it was confirmed that the lambda 1405 could not be accommodated in quark model, because this lambda 1405 in quark models systematically was predicted to have a too high mass. So what happened around the turn of the century? Around the turn of the century, there were some measurements actually by KK of the chaonic hydrogen shift and width of the 1s state that were conflicting. This measurement is very important to learn about the K-bar and interaction. So these conflicting experiments were were there for some years. During this time also, the DALI-1 idea of the quasi-bound meson-baryon interpretation of the lambda 1405 was reformulated in terms of effective chiral unitary theory in coupled channels in S-wave by these papers, including essentially a few channels, the first paper that gave the first idea, and the second paper essentially included the whole meson-baryon channels that can be included with the SU3 multiplets. Okay. For the next 10 years, then there was a very intense theoretical work. The next to leading order Lagrangian was incorporated, the S channel and new channel Born terms also were included, and many works, many more than the ones that are here listed. But they found similar features, that the K-bar-N scattering data was reproduced very satisfactorily, and that the lambda 1405 developed a two-pole structure. If you put you go to the Web of Science and insert the word lambda 1405, you will see how the interest of the lambda 1405 has been increased over the years in these two graphs. In the top one is the total number of publications listed in the Web of Science under this topic. And in the bottom graph, you see the citation times. And from the time that the lambda 1405 appeared in the PDG and for many years, the situation and the citation, I mean, these two graphs are basically parallel or correlated. So the situation was steady, normal. I mean, that represented some impact, but the impact really increased when the chiral unitary theories emerged, and then the increase is pretty fast, and essentially the interest for the lambda 1405 has kept constant. But an important point here was the measurement of the chaonic hydrogen by Siddhartha. This is an important experiment, and so now we go to the period of after 2005. In Siddhartha measured the energy shift and width of the 1s state in chaonic hydrogen, and that fixed the K- proton scattering length with a 20% precision. Moreover, in this period, there were various important experiments to understand the lambda 1405 line shape and its two-pole structure. There were experiments on photo and electron production, LEPS, and at class. Here is some result that obtained at class with the shape of the lambda 1405 with different pi sigma channels. But there were also studies in PP reactions at COSY and HADES. With all this activity, this triggered a lot of interest for the theoretical models, because now all this new and improved data helped to constrain the theoretical models better. And there was a proliferation of works, and this maintained the interest on this problem alive. And if we go back to these plots with all this experimental activity here, we see that the interest for the lambda 1405 has been sustained over the last 10, 15 years, because there are about 20-25 papers annually, and about a number of around 1,000 citations also annually. Okay, so now that I have convinced you that the lambda 1405 is a topic of interest, and that this is very much related to the K-bar-N interaction, I just want to move towards our chiral model. And the Barcelona group has contributed to this process of model improvement over the years, always having the focus on constraining the next to leading order pieces of the Lagrangian better. We have studied reactions that are especially sensitive to next to leading order terms, because in this reaction, the lowest order contributions vanish. For instance, this type of reactions. We have analyzed interplay between the Born terms and the next to leading order contributions. And we have studied isospin filtering reactions that are especially sensitive also to the next two leading order terms. What we want to do now or before moving. So for instance, in this last work in which we studied isospin filtering reactions, we did feeds in which we incorporated some isospin filtering reactions. I want to show you predictions from, I mean, in this work we have done some feeds, and these are predictions. Predictions that are not included of data that are not included in the feeds. This is, for instance, on the left-hand side, we see a prediction for the reaction K0 bar long proton into K plus cascade 0. This is a reaction that is pure isospin 1, is a pure isospin 1 process. And this could be measured at JLab. And actually there is a proposal by the KLF collaboration of using a secondary K long beam in order to study these kind of processes. As you see, one of our models, let's just look at the model in which has the gray band error area. This model is not, these data points that are only 2 data points. These data points were not included in the model, and our model reproduces pretty well this behavior. Also on the right-hand side, I want to show you some plot that has already been seen in this conference, and is the prediction by several groups of the K minus N to pi minus lambda amplitude. Is also a pure isospin 1 amplitude. And our prediction is this part in black, and the Amadeus experimental data is shown here in red, along with the prediction of other models. Okay, now we want to move forward. So our next step is to try to incorporate the terms beyond S-wave. Actually, all our previously developed K-bar interaction models are in S-wave. However, as we will see, the different terms of the Lagrangian contain higher partial waves, and I will report on new feeds that take these terms into consideration, for the moment up to P wave. Why we want to study P and higher partial waves? One obvious reason is because we want to explore the limits of the chiral model. If the chiral model has P waves, let's see what they do. Another one is we want to extend the description of the theory also to higher energies above the meson baryon threshold. We also want to investigate if dynamical resonances may appear beyond those observed in S-wave. And we want to extend the K-bar N interaction to higher momentum, because this will be important to understand, or because this momentum can be acquired by antichaons when they penetrate in the nuclear medium. And that has important astrophysical consequences. So, having given you the motivations why we want to study P and higher partial waves, let's see, or let's kind of remind you, I'm going to remind you previous work that include P waves in the chiral Lagrangian. Actually, there are not so many. There is a work in the STRANgeness S=0 sector, which is not our sector. There is, which is in the 2000. There is also a useful work for us in the STRANgeness S+1 sector in 2019. And in our sector, the sector that we are studying, which is the STRANgeness -1 sector, there is a work in 2002 in which I was involved, but this work only uses the lowest order Lagrangian. And in this work, there was not, I mean, it was not, the P wave did not have a very strong effect. And this was understandable because only low energy data was considered at that time. But it was very useful. It has been a very useful work for us for the theoretical developments that we have done in the work I'm going to present to you. And lately, there is a work by May, Dering, and Sadasivan, in which, in 2019, in which both the lowest order and next to lowest order Lagrangians are incorporated. So it's very interesting because they find a dynamical P wave pole in this channel, in the J parity 1/2 plus. But in the discussion, they already say that this resonance, this pole that is found in a dynamical way, mimics the lag of the sigma star 1385, which is would appear in the JP equals 3/2 plus. Okay, so the field is moving, and we want to contribute to this movement. Actually, in this work, they neglect certain next to leading order terms that we incorporate. Okay, so now a few strokes of the formalisms. And what we want to do is to derive an interaction kernel that consists of two diagrams. This consists of 4 diagrams. These diagrams are derived from the Lagrangian up to next to leading order that contains the lowest order, which is here, okay? And in the lowest order, this lowest order generates the Weinberg-Tomozawa term, the first one, and also the direct and cross-board terms, these second and third one diagrams. For the next to leading order diagram, we only consider the contact term is this lengthy expression, and this will generate this contact term of the next to leading order Lagrangian. And I just want to know that there are some terms here involving G's and H's that are new terms that are taken into account with respect to previous works. These terms are normally neglected because close to threshold, they are really small. But since we want to move beyond threshold, we think that it's better to consider them. Okay, let me move a little bit forward and see from these Lagrangians, then we derive interaction kernels. We see here the Weinberg-Tomozawa term. And as you look closely at these expressions, you already see, for instance, that the Weinberg-Tomozawa term contributes to S and P wave because you have here this type of products of two momenta. Okay, here's the scalar and the vector and the vector product. Then in the next two expressions, we see the direct board term, which is a little bit more complicated, but at the end it depends on S and on the same terms, which are really terms that contribute, these terms contribute to P wave and the other terms contribute to S wave. So this term also contributes to S and P waves. As for the crossed board term, which is here, it doesn't look much more different from the direct, but there is a difference here is that it depends on the U invariant, and this U depends on the angle, and that makes that this term already contributes to SP, D, waves, etc. And finally, the expression of the next to leading order diagram, which is here, as you see here also terms of the type Qj, Qi to the square and things like that. This is a complicated term that also contributes to SP and D waves. Our model essentially, what we do once we have the amplitudes for the 4 different terms, we need to incorporate unitarization. The 4 and 3 level amplitudes have this shape essentially, and now what we do is to partial wave decompose the different components, the spin non-flip and the spin flip amplitude into partial waves. And then these partial waves that are proportional to Legendre polynomials or its derivative, these partial waves need to be recoupled into well-defined total angular momentum, J, which is a conserved quantity. And these are the expressions that perform this recoupling. Once you have the amplitudes in good quantum numbers of J value, then you can unitarize. And what we do is unitarize the amplitude via the Bethe-Salpeter equation. And just want to mention that for this expression, an on-shelf factorization has been employed. In this equation, we see a quantity, which is the loop function, is the diagonal matrix of meson baryon loops, which is it is regularized using dimensional regularization. And therefore, it depends on some subtraction constants, which we come from the dimensional regularization scheme that we use, that are constant that also depend on a scale mu that we use about 1 GB. So we use mu equal to 1 GB for all channels. So once we have the amplitudes, then we can build our cross sections with this expression. And here we see the S wave contribution. Here we see the 2 P wave contributions. And here we see the 2 D wave contributions. Now this is the end of the model. But we need to fit the parameters of the model, which are listed here, the decay constant, the D and F axial vector couplings, the 14 coefficients of the next to leading order Lagrangian, and the 6 subtracting constant of the loops, because isospin symmetry is employed, and so we reduce those to 6. Okay, this parameters have to be fitted to cross-section data, threshold branching ratios, the Caronic hydrogen data, etc. What we do is a conservative approach. We fit to the same data employed in our last S-wave work because we want to see whether we can control these P-wave contributions. So this is the data that we use with the branching ratios that I define here, and some cross-section, elastic and inelastic channels, and also the data on the 1s Caronic hydrogen. I will present results for 3 different models. In the first model, one of the models is our old S-wave model, in which we use our lowest order and next to leading order terms in S-wave. And this is already what we publish in this reference, using the same data.
5 minutes.
5 minutes, okay. So the next to leading order Lagrangian, thank you, Abraham, does not contain here the H and G term. Then I will present also some results for a new S-wave model, in which is also a model in which only the S-wave are considered, but incorporate these new H and G terms. And finally, I will present results in which is the same as this model, is same as the previous fit, but incorporates the S and P wave contributions of the lowest order and next to leading order kernels. Okay, so the threshold observables are presented here, the typical ones, the gamma, Rn, Rc, scattering length, and the shift and width of the Caronic hydrogen. And as you see, the 3 different models, if you see closely, the 3 models do comparatively well at threshold. They are equally good if you take into account the error bars of the experiment. This is obvious because these observables are observables that are sensitive to the threshold, so where P waves are negligible. The same occurs if we look at the results of the cross-section for the classical processes. Here are the cross-section for K minus P, K minus P, to K0 bar N, etc., until pi 0 lambda. The results of the 3 models are pretty similar. I want to say that each different model is a different fit, which means different parameters of the fit. But as we see, the S-wave and the P-wave components, so the difference between the P-wave and the S-wave models is very is minor in these observables. Now I move to the cross-section for higher mass channels. For instance, the K minus P going to eta lambda, K minus P going to eta sigma 0, or K minus P going to K0 cascade of the K cascade channels, which are here at the bottom. As we see here, the P-wave model, which is the one in the solid black line, is doing better in some cases, for instance, here in the eta lambda channels, in reproducing some intermediate energy or even the higher energy region. Here for the eta sigma 0, we see the P-wave, of course, is very different from the other 2, but there is no data here, so this is not important. We don't know what will happen as soon as we get data here. But here in the K cascade channels, the P-wave model somehow is not doing very well at low energy, but really helps in going through the data at higher energies. Here also the same, no? In the higher energies, the P-wave model does pretty well, but okay. So this is what we obtain in our fits. But to see to have a better taste of the influence of the P waves, we have to look at these plots, at this plot, in which we separate, sorry, because there is a delay, we separate the individual partial waves from the S plus P waves fit. Here we see the contributions here in red of the S wave, in green and in purple, the 2 P wave contributions, and the 1/2 plus and the 3/2 plus. And for instance, what you see here in the eta lambda channel is that the 3/2 plus dominates. And for instance, here, the 2 P waves contribution in the eta sigma 0 are relatively small. In the K cascade channels, we see that the P waves especially the 1/2 plus, starts to get strength at higher, around starting at 2000 and moving forward. And in the K plus cascade minus, it is the 3/2 plus, the one that dominates. I want to point out here that if you analyze this, if you see what other more phenomenological model like the Born-Gachina models do in for these channels, they find a completely different behavior. For instance, here they find that this channel is dominated by 3/2 plus, and this channel is more or less 3/2 plus or 1/2 plus. So there are differences associated to the different scheme that you are using, and also obviously the different amount of data that you have fitted. So finally, I can show you, having fixed all the parameters in an S plus P waves fit, we can see the influence of the D waves, because the D waves are there in the Lagrangian. The parameters of the D waves we have already been fitted, are the same parameters that play a role in the S and in the P waves. And here you see the contributions of the 3/2 minus and 5/2 minus, which would be the D waves that we obtain. They are not fitted with the parameters that we have obtained in a fit that incorporates S and P waves. As we see, the D waves have a non-negligible role, and sometimes they also have an amazingly important role. So that really tells us that we need to incorporate a fit. So a fit incorporating also the D waves seems necessary, and this is work that is in progress. So here I summarize the results of our poles in S wave, because we only find poles in S wave. And with respect to the old model, we find the three in the isospin 0 sector, which is summarized here. We have the typical 3 poles, 2 for the lambda 1405 with similar coupling strength, and 1 for the lambda 1670 with a better prediction for the width. And also we find a pole in isospin 1, which is also a typical characteristics of these chiral models. But the energy can be very different from model to model. So our model does not generate poles in P wave, okay? So my conclusions are that the P waves of the Carré-Lagrangian influence substantially the cross-section of these reactions. The strength of the different partial waves might be considerably different than what is found, for instance, in more phenomenological approaches like the Born-Gachina fits. It is clear that the interrelated D waves that do not depend on additional parameters need to be incorporated in the fits. This requires, of course, to consider many more data points than the ones that we have used, higher energies, differential cross sections, etc. And we are now in the process of tackling this ingent task. But this task can only be done after the present work has shown that the incorporation of P waves does not spoil, actually rather improves the description of data with S wave contributions only. So thank you very much for your attention.
Thank you very much, Angeles. And I'd like now to open the floor for questions or remarks. Anybody just say something and I let you speak. Anyone in the audience. Let me then, I don't see anybody.
Eulogio is raising a hand.
Eulogio, please.
Thank you.
Speak up.
Can you hear me? Yes. Angeles, can you hear me?
Yes, yes, yes.
Okay, fine. So let's see, I mean, short and fast, I mean, the P waves, I mean, I didn't see them in there, but you still, I mean, do the JIDO work, no? I mean, putting explicitly the lambda, sigma, and sigma star poles, correct?
Yes, we do that in these Born terms.
Very good, very good.
But we do not include the sigma star.
You do not include the sigma star?
No, because we just take the chiral. I mean, it's a systematic work and see what we want to see is the limits of this Carré-Lagrangian. And this Carré-Lagrangian is built with the fields of the octet of baryons, so the sigma star is not there. We could, in the long run, put explicit resonances. This will have to be done, of course, but for the moment we are not there yet.
I think, I mean, it costs nothing, I mean, to put, you know, because it is
no,
exactly,
I know.
If you put,
okay.
if you put the lambda and the sigma star is the same. And, you know, I say that because this is related, I mean, to the work, I mean, of this Sadasian, Mai, and Derive. Because, you know, I mean, they do not put also the sigma star, but I mean, because they don't put it, I mean, they claim, well, I mean, it is a long story, but at the beginning they were putting effective Lagrangians and getting their, what they call a dynamically, I mean, generated stage in P-wave. So, I mean, Mikhail Dorin discussed that with me before, I mean, making any claim in public. And then, I mean, at the end, I mean, they concluded that it was just mimicking, as you said there, the sigma star. So I think, I mean, in view of that, I mean, I think it would be fine, I mean, to put the sigma star also in your.
Yeah, sure. I know in the long run, the sigma star and other resonances, explicit resonances
I mean,
that are not
least...
exotic. But we want to first explore the limits of the Carré Lagrangian with the basic fields, which are the octet fields.
Fine. Good.
Thank you.
From my own experience with playing with sigma star 1385 for the problem of dibaryons, and so I realized that its coupling to the K bar N channel is very small, and usually it's given very well in terms of lambda pi and maybe a little bit sigma pi, but the coupling to K bar N is quite weak. So you may be lucky in not incorporating yet, but in a systematic study, you need to probably check that or estimate.
Yeah.
Anybody else for remarks or questions?
Alex Chepley has raised the hand. Alex Chepley.
Alex?
Okay,
please.
First of all, thank you, Angels, for a really nice talk. I enjoyed it.
Hi, Alex.
And I also think that one should go now to higher partial waves before we get some new data. And I had similar concern, which was already raised, that it seems you are missing on this sigma star 1385, but I have also another concern, and it looks to me that you have quite plenty of parameters in your fits, and I suspect that you must get quite many competing local minima in your fits. Do you observe one global minimum, or did you check that you get more local minima and compare their predictions, for example, if they give different predictions for your parameters and experimental data?
I don't know really. I mean, the feeds are done by Albert, and also now they are. Daniel Gazda is also involved in using very complicated numerical procedures. So I don't know. I guess that you are right that there are local minima, but for the moment, the minimization that we are doing always bring you to the best minimum. But we have not explored the whole parameter space for the local minima, but we will have to do it. I mean, this is a very exploratory work. We are not claiming anything spectacular here. We have explored if we can control the P waves. Now we know that we have to do the waves too, and that implies also incorporating many more data that we have done, we have incorporated until now. And okay, I mean, we will do it and we will see how far we get.
If the chairman allows me to make a short comment on that.
I think we have a discussion time, and now we are past the time, so better stop now. Thank you, Andres, very much for your nice talk. And
thank you. Okay, now stop sharing.
We wait for you to take, and we go now to the next speaker, who is Ryuki Naomi, and he will talk about K bar N scattering amplitude measured below threshold. So here are the transparencies. Very good. I'll mention to you 5 minutes ahead of the end of the talk.
Okay, thank you very much for the introduction. So Andrew kindly introduced a nice review of the history of Lambda 1405. Today, I'm going to talk, discuss about the analysis of K bar N scattering amplitude based on the experimental data taken at the JPark. But unfortunately, we are now stepping on before the publication for some reason. So I really hope to join the introduction list of the Angela for the experimental data soon. So thank you. Now, in my lecture slide, this is the first appear of the Lambda 1405 in 1961. But as Angela said, that at this moment the name is not Lambda 1405. Actually, they call the Y star. Just this is a very poor statistic, but nevertheless there is a peak here. And now the PDZ value still refer the Lambda 1405 at 1405, based on the the analysis of the very old data. And as Angela already introduced, that recently intensively discussed the double pole structure of Lambda 1405, as you know. Then finally, PDZ refer the pole structure, a double pole structure of the Lambda 1405 as a review article written by these people here. Oh, I should use the pointer. Sorry, but sorry, pointer. But yeah. Here, they introduced the pole 1 and higher pole as a Lambda 1405, still Lambda 1405. This is the name. And the other Lambda 1380, the second pole, is referred. Still, the particle listing refer also the Lambda 1405 as previously. Then the recent discussion is still going on, and some authors claim that another solution for this species. So this object is quite related to the Caronic nuclear. The nature of the Caronic nuclei may be discussed in this workshop also. So there's the importance. I think that is quite important to study the low energy K-bar scattering data, even below the K-bar threshold. But how? So we propose the experimental data of this reaction, K-bar going to the neutron, and the neutron is knocked out the quad and recoiled back. Kaon is react to the residual nucleon and form the Lambda 1405. Then we can measure this reaction diagram, and here the K-bar N is the low energy K-bar N scattering realized even below K-bar N threshold. That's our motivation. This may be expected to be dominate the S-wave K-bar N scattering, and if we can finalize in the final state, it is pin down the isospin state of the final state, then we can study the most important channel of this isospin 0 channel. So I just briefly introduced the how extract the final state, and this is just a topological view how to distinguish the event final state of the pi sigma. Just flashed, and finally we identify the final state as n pi plus pi minus n for the charged mode. Then we can reconstruct the invariant mass of the pi sigma state. Then, but there are some background processes come from the forward sigma production as well as the K0 production. This is the same final, produce the same final state. But we can successfully reject by making this kind of peak. And yeah, and also the most important channel is the neutral mode, but it's quite difficult to distinguish. But we can detect this charged mode together with the knockout neutron. And a missing mass of this particle can be identified in this way. But we are now stepping on how to distinguish the event, the background event, identify the background event, which affect the contamination of the final state of the pi 0 sigma 0 processes like this. So this is the reason why we are stepping on. But I believe that the analysis is very close to the end. So this is more detail. Okay, I can skip. And also we can also the knockout proton instead of the knockout neutron at the forward angle. Then we can also measure the isospin 1 state. So as this is the okay, to detail. And this is our current result of the obtained spectrum. The horizontal axis is a pi sigma missing mass, and the green line shows the K minus P mass threshold. And the here left panel is the so-called charged mode, which contains both isospin 0 and 1. And the right panel shows the pure isospin 0 channel and the isospin 1 channel individually, but still very linear. Okay, so and maybe we can recalculate to extract the isospin 0 mode for comparison. So this mode show this charged mode minus a pure isospin mode may be corresponding to the isospin 0. And we had a very similar shape, but the strength is a bit deviate to some extent. So now I will introduce the preliminary analysis of this spectrum shape by doing this way. So we just consider the two-step processes as I showed in the previous slide. And also the one-step processes considered. But maybe we just detect the energetic neutron at the forward angle. So maybe this process is reduced. So, and this diagram can be expressed by this way, and detail can be skipped, but we can decompose into the scattering amplitude come from the second step processes times the response function of the come from the first step reaction on the deuteron. Then we just estimate this response function by calculating this way. At all the formulation is written in here. And scattering amplitude of the first step can be is available by partial wave analysis by Roper et al. But anyway, by doing so, this is the just demonstration how the partial wave analysis work. And this is the so-called the response function of the first step. So this is important. And actually, this shape is characterized by the observed spectrum shape like this. Okay. Sometimes we call this is like a quasi-free-like structure as the hypernuclear spectroscopy. So sometimes different called this way. So okay, then okay, I'll skip. I just demonstrated the first step reaction is work by fitting the quasi-free reaction of the quasi-K0 production data. And then we are interested in the second step amplitude can be described by so-called the effective range expansion method to maybe to the second order expansion of the scattering amplitude, and the parameter has 3 parameter and 2 complex parameter called scattering length and effective range and phase. Fact. This is real, but and if we take the amplitude, this cross section, maybe this phase disappear. Okay, then we can obtain the this scattering amplitude this way, and the product of these two response function and scattering amplitude. Then we can fit our spectrum by this way, and we can determine the parameter of the scattering amplitude and effective range by this way. This is still preliminary, I should say. And then by doing so, and we can extract the scattering amplitude of the off-diagonal part of the scattering amplitude in 2 channels. Then from this parameter, we can extract the diagonal part. Then the scattering amplitude, the energy dependence of the scattering amplitude can be described, plotted this way. Here, the crossing, the real part, the behavior of the real part is crossing 0 here. I should, I'm sorry. I should plot this data. Sorry. Sorry. And then we can obtain the pole position at here is around 16. This is rather consistent with the analysis of the chiral unitary model. So this is summary. So we just extract the pole position of lambda 405 based on the line shape analysis of the effective range expansion method, and we just obtain the so-called the higher pole is the rather consistent to the prediction model. Okay, that's it. Thank you very much.
Okay, thank you very much. We have some more time now for questions or comments. I can't see hands in my.
Yes, there are
apparatus,
hands.
so
There are hands there.
Speak
Yeah.
up. Ulogio, do you wish to make a
Yes.
remark?
Thank you. Yeah.
Please go ahead.
Okay, since there is time for discussion, let's see. I mean, you had, I mean, one competing mechanism, which in page 21, where you have the impulse approximation that it goes also to pi sigma, correct?
Pi sigma.
Yes,
Yeah.
pi sigma. I mean, but you know, I think your kaons are energetic, correct? So
Yes, yes, yes.
Then I mean,
kaon. You are talking of the incident kaon
yeah,
or
I mean,
record
no,
kaon?
21, page 21, where you have the mechanism in which the pi sigma are produced there in the upper. That's it. Yeah.
Yeah,
Right.
yeah.
This should
Yes.
not be competitive, you know, because your kaon, I mean, is energetic, and then the pi sigma that comes there, I mean, it is very, very far away from the region of the lambda 1405. So you can take that into account if you want in the analysis. But I mean, the variant mass of this pi sigma is so far away that you can forget about.
Yeah,
That's
yeah,
my opinion. Okay. The important one is the lower one. This diagram that you have there, the rescattering, right? And then, I mean, there's a question here. I mean, because, I mean, of course, you can see there that what you have is k bar n going to pi sigma. So from where do you extract k bar n going to k bar n, which you put there at the end? You said at the end, you show us, I mean, the figure in which you had the amplitude for k bar n going to k bar n. So
yeah,
I mean,
this one.
no, another
Yeah.
one. I mean, what do you
Thank
get
you.
it from? What do you
Thank
get
you for
it
the
from?
question.
Where do you get it from? I mean,
Yeah. That is the background actually.
K bar n going to K bar n. I mean, you don't
Yeah,
get that
K
from
bar
this
n,
reaction, no?
Yeah, this one, this process.
No, I mean, you show at the end, I mean, it doesn't matter. You show there at the end, I mean, that you get from this reaction the K bar n amplitude going, K bar n going to K bar n.
Final said. Okay.
And I don't know, where do you get this information from this reaction?
Yeah. We just assumed two coupled channels
okay.
here.
You are making assumptions, okay, because the experiment doesn't give you this amplitude.
Yeah.
And then the last comment, and with this I finish, is, you know, that, I mean, this occurs in the deuteron, and of course, I mean, you know, I mean, Sekihara and Jido were the first ones, I mean, to do the
yes.
analysis of that. And then, I mean, sure, I mean, you have there the shape of the lambda 1405, but you also have the deuteron wave function, I mean, that one has to take into account. So, I mean, the wave function of the deuteron is not innocent. It's not innocent in this reaction. It plays some role. So that's why I say that the proper analysis of your data would require the help of some theoretician. And for that, I can recommend, I mean, that you convince, I mean, Sekihara again to redo the calculations, because, I mean, he has the ability, I mean, to calculate that very well. And he also has the best models.
Yeah. Thank you very much for the comment. Actually, I just refer the same wave function as they used.
Yeah, okay, good. Very good.
Okay, the point is well taken. So anyone else for remarks or questions? So nobody is speaking up. So I'd like to thank again the speaker for this nice and brief presentation. And
thank you very much.
Let's go now to the last speaker of this session, Diana Sergi. She will talk about experimental studies of the K nucleus at low energies, including kaonic atoms. Please go ahead.
Buongiorno, good morning, can you hear me? Can you hear me?
We hear you, I don't see you.
Yeah, we hear you.
You can hear me, okay? May I, now I'll share the screen. Can you see my screen?
Very good, yes, we see. Please go ahead.
Okay, I'll go ahead. Okay, good morning. Before starting my presentation, I'd like to thank to the organizer for giving me the opportunity to participate to this workshop. My presentation is dedicated to the experimental studies of the kaon-nucleus interaction at low energy with X-ray spectroscopy of kaonic atoms, the Siddhartha 2 experiments, and future perspectives. DAVNE, as we already know, it's an electron-positron collider in which the low momentum monochromatic counts are coming from the decay of the free resonance produced by the electron-positron interactions. For this reason, DAVNE is a collider which is suitable for the low energy count physics like the Caronic atoms and Caronic nuclei interaction studies. And my talk is dedicated to the Caronic atoms experiment. This kind of measurements are done in the framework of the Siddhartha and Siddhartha 2 experiments. Siddhartha 2, it's an international collaboration. The list of the participating institutions are quoted here together with the list of the funding agencies. The Siddhartha 2 experiment is an extension and an enrichment of the previous experiment, the Siddhartha experiment, which was ending its data campaign in November 2009 after having performed Caronic atom transition measurements. In the Siddhartha 2 experiment, we are measuring the transitions which are occurring in the cascade process of the Caronic atoms, because this kind of measurements represents a fundamental study of the strong interaction between the anti-kaon and nucleus at low energy limit. The scientific aim of the Siddhartha 2 experiment is the determination of the isospin-dependent anti-kaon nucleon scattering lengths through a precise measurement of the shift and the width of the K-alpha line of kaonic hydrogen and the first measurement of the kaonic deuterium. In the case of the kaonic atoms, as we already know, the strong interaction between the kaons and nucleus will determine a shift in energy of the last levels from their pure electromagnetic value and a finite lifetime of the state corresponding to an increase on the observed level width. For the kaonic hydrogen and kaonic deuterium, the K-series transition are of main experimental interest since they are the only one affected by the strong interaction. The electromagnetic interaction with nucleus is very well known, and as you can see, the energy levels can be calculated at the precision of electron volts. So even a small deviation from this electromagnetic value will allow us to get information on the strong interaction between the kaon and nucleus. In this table, one can see the atomic binding energy for the light systems are in the keV range. Namely, the kaon interacts with the nucleus with a relative energy of the few keV instead of tens of MeV, as is in the performed low energy scattering experiment. For that reason, kaonic atoms offer the unique opportunity to perform experiments equivalent to the scattering at vanishing relative energies. This allows determination of the anti-kaon nucleus interaction at threshold without the need of extrapolation to zero relative energy. Here we have a list of the Siddhartha results. In 2009, Siddhartha performed most precise measurement of the kaonic hydrogen and the first exploratory study of the kaonic deuterium. Here we have the kaonic hydrogen spectrum, where you can see the K-series lines. As you can see, the results obtained for the shift and the width of the 1s state in the kaonic hydrogen by the Siddhartha represents the most precise measurements done until now. Moreover, Siddhartha measured for the first time in a gaseous target the X-ray transition for the kaonic helium-4 and for the first time ever the X-ray transition for the kaonic helium-3. As you can know, the shift and the width of the kaonic X-ray energy have been measured using the atomic targets with atomic numbers from 1 to 92, and these data are systematically well understood using the optical potential model only for the kaonic atoms with zeta greater than 3. The complicated story of the kaonic atoms with zeta 1 and 2, for which we have no data or were very poor data, not in a good agreement with the theory, started for the kaonic hydrogen and kaonic helium in 1970s. It was continued by the experiments which were done in 2000, in which it was found a good agreement with the theoretical data. But what is still missing is the measurement of the kaonic deuterium, and this will be done in the framework of Siddhartha 2 experiment. The scientific claim of the Siddhartha 2 is to perform a precise measurement of the kaonic deuterium to determine the X-ray transition to the ground state, such to measure the shift and the width induced by the strong interaction. The desert relation, including the isospin breaking correction, connects the shift and the width of the 1A state epsilon 1s and gamma 1s to the real and imaginary part of the AK minus P and AK minus D. Since the measurement of only kaonic hydrogen does not allow to extract the A0 and A1 scattering lengths, the analysis of combined measurements of the kaonic deuterium and kaonic hydrogen will allow us to extract the isospin-dependent anti-kaonucleon scattering lengths, which represents fundamental inputs of low-energy QCD effective theories. Siddhartha-2 is a development both on the detector side and on the target side. The goal of the new apparatus is to increase the signal to background ratio and also the signal rate by gaining in a solid angle and taking advantage of the new SDD, and also to reduce the background by improving the SDD timing and implementing additional veto systems. Why this? Because as we know, for the first exploratory measurements done for the kaonic deuterium by the Siddhartha and from the theoretical prediction, the yield of the K-alpha line in kaonic deuterium is at least 1 order of magnitude smaller than the kaonic hydrogen yield. For that reason, an enhancement by 1 order of magnitude of the signal to background ratio is required to the Siddhartha-2 apparatus. Here we have, for example, a list of the major upgrades and optimization done for the Siddhartha-2 setup with respect to the previous setup. For example, we have new interaction region in the Daphne accelerator, which is dedicated to the Siddhartha-2 experiment, with the new focusing and quadrupole magnets, which are much more performant like in the past. We have a new beam pipe, which is done by carbon and aluminium. With the new beam pipe, the flanges were removed. These flanges was the major source of the asynchronous background in the Siddhartha experiment. Moreover, we did a lot of, we have a new cryogenic new vacuum chamber, new cryogenic system. We have new cryogenic target. The new cryogenic target has an working point of 30 Kelvin and a maximum working pressure of 0.3 megapascal. This will allow us to almost double the gas density with respect to the Siddhartha. And in this way, we can increase the stopping power of the counts in our target. We have a new type of silicon-3 detectors. These new silicon-3 detectors were developed by the FBK. The SDD array consists of 8 square SDD cells, each one having an active area of 8 by 8 millimeter square, arranged in a 2x4 arrays format, only with 1 millimeter dead area region along its border, and this array is placed on an aluminum ceramic. More details regarding these detectors, how they are functioning, the properties of these detectors will be given in the talk of my colleague Francesco. Finally, in our setup, in the Siddhartha-2 setup, we will have 48 monolithic SDD arrays, which will surround the target with a total area of around 246 centimeters square. In the Siddhartha-1, we have also, in the Siddhartha-2, have also 2 veto systems. One veto 1 system, which is placed outside of the vacuum chamber. It consists of outer barrel of scintillators acting as gas stopping detector, and we have the veto 2 systems, which is consists of inner ring of scintillator tiles placed as close as possible behind the SDD detector for charged particle tracking. Here it's an image, a schematic view of the Siddhartha-2 setup. And here we have some, let's say, some picture with the installation of the Siddhartha-2 setup in spring 2019 in the Daphne accelerator. And presently we are in the phase 1. Phase 1 with Siddhartino, which means during the commissioning of the Daphne, we are doing optimization with the Siddhartino setup for the kaonic helium-4 measurements with the aim to confirm when the Daphne background conditions are similar to those of the Siddhartha 2009. What it is Sidartino? Sidartino is the Siddhartha setup, Siddhartha 2 setup, in which we install only 8 SDD arrays, aiming to measure the Caronic helium in order to quantify the background in the new Daphne configuration before the measurements of the Caronic deuterium. The more details regarding this, the Sidartino setup, the results obtained with the Sidartino setup are included in the talks which will be given by my colleague Marco. Here in 2009, we measured the Caronic helium L-alpha line transition with the Siddhartha, with a very nice signal to backgrounds 10 to 1. We want to improve this signal with the Siddhartha 2 and to bring it to 100 to 1. During this phase 1, we are doing a lot of work. We work with the Sidartino setup inside the Daphne. We are doing optimization of the silicon detector, of the trigger, optimization of the data acquisition, optimization of the calibration procedure. The details you'll see in the next talks. We are doing refined optimization of the luminosity detector and the cross-check with the Daphne luminometer. And this, regarding the luminosity detector, you'll find much more details in the talk of the Fabrizio. We are doing background reduction and optimization together with the Daphne for Caronic atoms measurement, and maybe we will have a test run with Germano detectors in parallel with Sidartino. Here it's an email, a picture with our part of our collaboration in April 2019 after the Siddhartha 2 setup was installed in Daphne accelerator. When the phase 1 of the Siddhartha 2 will be closed, and this will be in this summer, we'll pass to the Siddhartha 2 phase. In the Siddhartha 2 phase, if the phase 2, we will install all the 48 SDD arrays inside the setup, and we will start the measurement of the Caronic deuterium for a run of 800 inverse picobarn, starting for the autumn of 2001 and in 2002. In the first run, we Siddhartha 2 setup as planned. We will integrate something like 300 inverse picobarn. In the second run, with optimized shielding, redoubt electronics, and other necessary optimization, we'll integrate something like 500, the remaining 500 inverse picobarn. A detailed Monte Carlo simulation was performed in Jan 4 for the Siddhartha 2 setup. In the Monte Carlo simulation, we are using like assumptions the values for the shift and the width of the 1s ground state of the Caronic deuterium, like minus 800 electron volt for the shift and the 750 electron volts for the shift, for the width. And this figure is shown the expected spectrum for an integral luminosity of 800 inverse picobarn. The extracted shift and the width can be determined with a precision of 30 electron volt for the shift and 80 electron volt for the width. And this precision, as you can see, are comparable with those obtained for the Caronic hydrogen and will allow us to extract the anti-Caronic nuclear isospin-dependent scattering lengths. Different theoretical calculation on the shift and width of the 1s ground state of the Caronic deuterium were performed in the last year, as you can see in this figure. The expected precision of for the Siddhartha 2 experiment is quoted in this red rectangle. The experimental results will set constraints to the theories and will help us to disentangle between different theoretical approaches. The Siddhartha and Siddhartha 2 experiments on Daphne Collider, as I showed, provide unique quality results for the understanding of the low energy QCD in the STRANgeness sector. But since Daphne confirmed to be a unique machine in the world to perform fundamental physics measurement at the STRANgeness frontier, we propose for future a series of measurements to be performed at Daphne with a strong impact in many sectors our fundamental physics, like strong interactions, a QCD theory of the strong interaction in low energy regime, astrophysics, dark matter studies, fundamental physics. Let's say a possible schematic schedule of the proposed measurement is shown in this Gantt chart. For what regards the fundamental physics with the kaonic atoms, we propose a series of kaonic atom transitions to be measured. And I'm referring first to the heavy kaonic atom transitions, since these atomic transitions have a strong impact to solve the charge kaon mass puzzle. As we know, there is a large uncertainty in the kaon mass, and also there are discrepancy between the two experiments which give the kaon mass value. In this direction, we plan to do some measurements using high Z targets, which can be used to measure transitions both for the high level and to the low end levels. In the case of the low end level, we can obtain some results regarding the multinucleon interactions. In the case of the high end level, since this high end level, since these transitions are purely QAD, we can have some information regarding obtain information about the charge kaon mass problem. We want to use this kind of targets like selenium, zirconium, lead targets. And since all these transitions, as we saw, are covering a very large spectrum from few hundred keV up to few MeV, in order to measure this kind of transitions, we propose to use germanium detectors. These germanium detectors has a very huge capability up to 100 kilohertz, and for that reason we can place it near to the interaction point in the Daphne to maximize the geometrical efficiency and to do in future this kind of measurements. For what regards the case of the light kaonic atom transitions, and this light kaonic atoms transition have an impact on the kaon nuclei potential and on the chiral models below the threshold. We plan to perform measurement using targets like this one, like helium-3,4, lithium-6,7, beryllium-8,9. This measurement to be performed on the both low level and high level transitions with the energy range between 10 and 100 keV. We plan to perform this measurement using two Siddhartha-like setup in parallel, one which is placed above and the other below Siddhartha, below interaction point. A schematic view of the setup is shown here. In the first setup, which is dedicated to the lowest energy region, we plan to use a silicon detector 1 millimeter thick, having a large efficiency between 10 and 40 keV range. In the second setup, we are planning to use a cadmium zinc telluride, which will concentrate to the transitions from 40 to 100 keV. The 1 millimeter thick silicon detector is already built in collaboration with FBK. For what regards the cadmium zinc telluride detectors, this will be developed in the STRONG 2020 Astra project, and the first prototype will be available by mid of 2022. For what regards the sub-electron volt precision measurement of the kaonic transition, this can be done using the mosaic crystal based on von Hamon spectrometer, which are developed in the framework of the VOXES experiment. I will not enter in detail regarding this because it will be a dedicated talk to the VOXES experiment by my colleague Alexandru Scordo. For the case of the kaon nuclei scattering and interaction, as we know, the present knowledge of the total and differential cross-section of low energy kaon nucleon reaction is very limited. Below 150 MeV/C, the experimental data are very scarce and with large errors. So the kaon nucleon scattering interaction data are fundamental to validate theories like chiral symmetry, lattice calculation, potential models. All the present proposal for future of Daphne Collider are described in detail in this document, which can be found at this web address. The goal of this document is to present to the scientific community our plans and to stimulate a discussion in order to optimize and integrate our strategy, and also to invite all those persons which are interested to participate to this new adventure in the STRANGeness physics. So here we have some theoreticians, a list of theoreticians which already provide some input for this future of Daphne. To this theoretician, there are added another groups from 11 countries. And in the end, I would like to close saying that we strongly believe that this is an opportunity which cannot be missed, since we propose to measure the fundamental interaction process, which could not be measured till now, and which will have a huge and concrete impact on the nuclear physics, astrophysics, and cosmology. Thank you very much.
Thank you very much, Diana, for keeping on time and giving us a clear picture of the vision of Siddhartha and the lab in general. Now we have plenty of time for questions or remarks or other views. Anyone wishes to speak, please. Well, if not, probably we'll hear more of the experimental situation in the session after the break. And I thank you and all the previous speakers, the two previous speakers in this session, and I close this session.